Dear students, after seeing the difference between the cold working and hot working, now I am just want to focus some important factors for the recrystallization temperature. Some important points, rather we can say, we will see for the recrystallization temperature. So the factors affecting recrystallization temperature. So first point I will write the purity of the material. Purity of the material. So see here, the recrystallization temperature is generally low for the pure material and it is high for the alloys. If I write here the recrystallization temperature for the pure metals or materials, it is 0.3 times the melting point temperature of this material. Whereas if I write the recrystallization temperature for the alloys, it is around 0.6 times the melting point temperature of that material. So this is the first thing, very important. Second, if I talk, the recrystallization temperature is a function of time. The function of time, or I can write here the point heating time. Heating time. So see here, if you are having the slow cooling rates, that is nothing but the heating time is high. Heating time is high. So for the slower cooling rates, the recrystallization temperature is lower. Please remember, for the slower cooling rates, we are having the minimum recrystallization temperature. Third thing, see, if prior to cold work, okay, the recrystallization temperature decreasing. Okay, so when we are working on the material and prior to that the working is done on the material, then the recrystallization temperature goes on decreasing. That is, prior to cold work, the recrystallization temperature goes on decreasing. It is because of, see, so whenever we increase, or I can write in the fashion like this, when we increase the degree of cold work, recrystallization temperature goes on decreasing. So if I write like this, note down these points. As the degree of cold work increases, the recrystallization temperature decreases. Actually, see, when the degree of cold work goes on increasing, the number of dislocations are increasing. The number of dislocations are increasing, and these dislocations are going to store the huge amount of energy. So because of that, there is the increased or huge amount of stored energy. And when we are going for the further cold working or further working on the material, this energy is supplied by the stored energy by diffusion process to this recrystallization. So the stored energy is supplied through what? Diffusion for the recrystallization, and because of that stored, and because of that the recrystallization temperature is lower. So that is the reason why. So degree of cold work increases when we increase the working on the material, its recrystallization temperature comes down. So that is the important thing. And of course, very important, the recrystallization temperature depends upon the melting point of the material. Okay, so these are some points which are very, very important. We have to keep it in mind for the recrystallization temperature. So this point we can again explain in such a fashion that, suppose this is the component A and this is the component B. It is subjected for cold working and it is subjected for hot working. Say the initial thickness of this plate or component 10 mm. Okay, now it is having some initial recrystallization temperature. When it is undergoing deformation, say I have this component, say A dash to 5 mm thickness. Same fashion here, I have deformed this component B to the 5 mm thickness by using the hot working. So definitely, see here, now this further deformation, the recrystallization temperature has been changed in case of this cold working. Okay, so here the recrystallization temperature, that is prior to cold work, if you go for further deformation, this recrystallization temperature for A dash is definitely lower than the recrystallization temperature for the A. Please remember, this is for cold working. For hot working, it is not like that. It is generally same recrystallization temperature even to the prior to the hot work. So please remember this. So यहाँ पे जितना आप कोल्ड वर्किंग बढ़ाते चले जाओगे, recrystallization temperature उतना ही क्या होता चला जाता है, कम होता चला जाता है. As the number of dislocations are increasing, they are storing the energy, and whenever it needed for the recrystallization, they will supply that energy through the diffusion. So that is the thing. So please remember these important points about recrystallization temperature. Dear students, we know that in the metal forming process, the stresses are induced beyond the yield strength of the material and below the ultimate strength of the material. So to have the maximum possible working onto the component, so this plastic deformation zone from sigma y to sigma ultimate, that zone must be get wider, then we can have the maximum working on the component. So if you look at this stress strain diagram, so in this diagram, so this region from, say, this is sigma y to this sigma ultimate, stress versus strain I am talking, this is the yield strength and this is of course ultimate. So this zone must be wider, isn't it, to have the maximum working on to the component. So this plastic deformation zone should be wider, and to widen this zone, so there are the two ways we can have. So one is, so we have to increase the ultimate strength of the material, increase the ultimate strength of the material. How to do that? By increasing the cold work, by increasing the cold working on the component. Okay, and the second way is to decrease the yield strength of the material, yield strength of the material. And how to achieve this? We learned that heating the material above RCT, heating the material above recrystallization temperature always decreases sigma y, isn't it? We know that. That is, material become ductile, easy for deformation. We can heat the material above the recrystallization temperature, so sigma y, yield strength of the material, goes on decreasing. Now out of these two, suppose we have this first option, that is to increase this ultimate strength of the material by increasing the cold work. So if I increase this sigma ultimate from this first condition or option, so of course sigma ut is going to increase, but in the amount the sigma ultimate has increased, in same amount you can have here increase in the sigma y also. So yield strength of the material also goes on increasing in the amount where the sigma ultimate increased, isn't it? So resultant, if you see, so the width of this PDZ is same again. So जितना अल्टीमेट स्ट्रेस बढ़ रहा है उतना ही सिग्मा वाई उतने अमाउंट में बढ़ रहा है. सो डेफिनेटली नेट जो इंक्रीज है वो क्या है? जीरो. So PDZ remains same only. It is not get widened. So by using this first option, that is increasing the ultimate strength, the PDZ is not getting widened. So we are not getting the extra or additional excess work onto the component. It will remain as it is, जितना possible है उतना. Now come to the second. So when we go on heating the material above the recrystallization temperature, sigma yield, sigma y जो है, yield strength जो है material की, no doubt it is goes on decreasing. But at the same time, the sigma ultimate is not showing that much increase in the ultimate strength. Negligible decrease in the ultimate strength, and you will get this PDZ widen. Okay, so when you heat the material above the recrystallization temperature, the yield strength of the material comes down. That is, there is a chances of either improvement in the ductility. Material is easy to deform. It's having good formability. In this case, as there is no decrease, as there is no fall in the that much amount of fall in the ultimate strength, it results into the widening of the PDZ, and you can have the maximum amount of working on the component. So generally this option, it is get followed by many of the materials, that many materials shows the decrease in yield strength when they heated above the RCT, except the steel. Why steel? Because we know that steel is having the allotropic forms. So it is at room temperature, at higher temperatures. Say if I talk about the alpha iron and delta iron, they are having the body centered cubic structures. But they possesses, if you have the gamma austenite का क्या है crystal structure? It is the face centered cubic structure, isn't it? So at different temperatures, the microstructure, the crystal structure of the steels is different. That is allotropy of the steel, or it is also known as the polymorphism. Because of that, steel is having the certain ranges of temperature where it can have the very good ductility, or it can have the poor ductility, or they are very difficult to deform. So which are these ranges actually if you talk about the steel? So the steel in the temperature range, say 150 degrees centigrade to 350 degrees centigrade. Then from the temperature range 400 degrees centigrade to 750 degrees centigrade. Then 800 degrees centigrade to 900 degrees centigrade, and above 900 degrees centigrade. Okay, so see, if we we are going on increasing the temperature in this range from say 150 degrees centigrade to 350 degrees centigrade, you will observe that there will be increase in yield strength of the steel. And the same thing we can observe from the region 800 degrees centigrade to 900 degrees centigrade. If you increase the temperature, the steel will show the increase in the yield strength. But the temperature range you can see here 400 to 750 degrees centigrade, if you go on increasing the temperature, the yield strength of the steel, please see here, it is goes on decreasing, and above 900, if you are increasing the temperature, the yield strength of the steel goes on decreasing. That is, in simple word we can say that the steels are very good very good to deform, to work in the temperature range where, so either in 400 to 750 degrees centigrade or above 900 degree centigrade. And it is difficult to work in the temperature range because the yield strength is increasing. We don't want the increase in yield strength. जितनी yield strength कम है, strength कम है, उतना हमको क्या है, ductility अच्छी मिलेगी. With little amount of forces we can deform the material. So see, in the temperature 150 to 350 degrees centigrade, it is difficult to work on the steel because the yield strength goes on increasing, and in the temperature 800 to 900 degree centigrade. Why it is so? Because of the allotropic form of steel, isn't it? Polymorphism. So in this way there are two ways actually to increase or to widen the plastic deformation zone. One is by increasing the ultimate strength and one is decreasing the yield strength. But which is most appropriate option that we are using generally, heating the material above its recrystallization temperature will decrease the yield strength of the material. Thank you.